Okay, hi everyone, welcome back to this video series introduction to firewalls, IPSec encryption. Many protocols in use today transmit data in clear text. Using clear text leaves your network open to packet sniffer attacks, in which case data packets are captured and viewed as they are transmitted across the network. Although some protocols such as HTTP provide the ability to use application level security through SSL. Many other protocols don't have built-in security mechanisms. The solution to this problem is to implement Internet Protocol Security IPSec. IPSec allows data to be encrypted as it is transmitted across the network. The following two protocols that are part of IPSec can be used to protect transmitted data. Authentication Header AH. AH provides authenticity protection to transmitted data by digitally signing each packet to ensure two things: that the packet is not modified in transit and that the originator of the packet is who she says she is. Encapsulating security payload ESP. ESP provides encryption services by encrypting the payload of each packet so that the contents of the packet can't be observed. In addition to the two protocols used by IPsec, you can use two modes to transmit the IPsec protected data. Transport mode is used to encrypt data as it is exchanged between two endpoints. The data encrypted at one computer or network host is decrypted when it arrives at the target computer or network host. Tunnel mode encrypts the data for only a portion of the distance between the source and target hosts. Generally, mode is used to encrypt data between network segments, and it is transmitted over an unsecured portion of the network, such as the internet. The configuration that determines what and over what path data is encrypted is known as a security association, SA. SAs are negotiated between computers, hosts, not between users. You can't configure an IPsec SA between two users on the network. It can be configured only between the computers that they use. Figure A3 shows how an IPsec SA is negotiated between a client and a server, where IPsec is configured to encrypt telnet sessions. The steps shown in figure A3 take place as follows. 1. The telnet client sends an initial packet destined to the telnet server. 2. The client computer's IPsec driver intercepts the packet before it is transmitted and compares protocol information with a list of IPsec filters. In this example, the client computer is configured to negotiate an SA between the client computer and the telnet server. The negotiated SA defines the IPsec protocol, the algorithms used for protecting the transmitted data, and the authentication protocol. To negotiate the SA, the two computers involved in the transmission of data must mutually authenticate each other. IPsec supports three methods of authentication: shared, secret, Kerberos, and certificates. The method that you choose may require additional firewall rules at the firewall to allow authentication packets to be exchanged. So I can see here IPsec transport mode encrypted data, IPsec tunnel mode encrypted data. Okay, so 3. The IPsec driver stalls the packets and instructs the Internet Key Exchange IKE to negotiate the SA between the client and server. 4. The IKE protocol is used to negotiate the necessary SAs between the client and the server. Both the client and the server use UDP port 500 for the IKE negotiation. 5. The IPsec driver is informed about the resultant SA so that it can encrypt, sign the data by using the negotiated algorithms before it is transmitted. 6, the IPSec driver applies the required encryption and/or integrity algorithm to the data and then transmits the data to the server. When does IPSec fail? Because of the security applied to data when IPSec protection is applied, IPSec can't pass through a firewall that performs network address translation, NAT. NAT replaces the original source IP address and port information in an outgoing packet with external address information. When IPSec is applied to a data packet, the source IP address and the source port address fields are protected fields. For Authentication Header, the modification for the source data invalidates the signature applied to the packet, and for ESP Encapsulation security payload, the source data can't be read because it is encrypted. What will the future bring? Currently, 2 draft documents are before the Internet Engineering Task Force, IETF, that propose a method for the negotiation of passing of IPSec packets through NAT devices. When a new standard is proposed to the IETF, the prerequisite for a common RFC document is known as an Internet draft. The first draft, IETF IPSec NAT TIKE 05.txt proposes a method for 2 hosts to negotiate IPSec NAT traversal. The draft outlines a modification to the Internet Key Exchange IKE protocol that would allow the 2 endpoints to identify whether NAT traversal is supported by these endpoints, and would also identify if one or more NAT devices exist between the 2 hosts. This modified IKE packet is sometimes referred to as NATD or NAT detection packet. NAT devices are detected by determining whether the IP address or port address in a packet are changed as the packet is sent between the source and destination hosts. This is accomplished by both sides calculating a hash that is based on the source and destination IP addresses and ports, and then comparing the results. If the results are the same, no NAT device exists between the 2 hosts. The current version of the draft negotiation of NAT traversal IKE draft IETF IPSec NAT IKE 05.txt is available at the time of this writing at www.ietf.org/I internet drafts/drafts IETF IPSec NAT IKE 05.txt. By the time you read this book, the draft may be updated with a newer draft or may have been released as a request for comment RFC. The second draft IETF IPSec UDP Encaps 06.txt proposes encapsulating the IPSec payload in a UDP header, which would allow the NAT device to translate the IPSec packets as they traverse the NAT device. This UDP encapsulation doesn't require firewalls or other NAT devices to do anything different when they perform NAT on outbound or inbound IPSec packets. This method is referred to as NAT-T or NAT traversal. The current version of the NAT UDP encapsulation of IPSec drafts IETF IPSec UDP Encaps 06.txt is available at the time of this writing at www.ietf.org internet drafts/draft IETF IPSec UDP Encaps 06.txt. By the time you read this book, the draft may be updated with a newer draft or have been released as a request for comment RFC. Transport mode for encapsulation. The UDP encapsulation of IPSec packet draft proposes the addition of a new UDP header between the original IP header and the ESP header the one added by the IPSec process as shown in figure 8.4. The UDP header is initially configured with both source and destination ports of UDP port 4500. The use of this port indicates that the packet is a UDP encapsulated IPsec packet. The UDP encapsulation of IPsec packets draft only supports ESP encryption. This draft includes no support for IPsec protection. When the IPsec packet passes through a NAT, the NAT device can now translate the original IP header and the newly inserted UDP header without changing the hash value created by signing the ESP header, TCP, UDP header, data, and ESP trailer. Tunnel mode ESP encapsulation. The UDP encapsulation of IPsec packets draft also includes documentation on how to pass IPsec transport mode packets through a NAT device. For tunnel mode, the original IP packet is encapsulated as shown in figure 8.5. The proposed tunnel packet construct differs from a typical ESP tunnel mode packet through the addition of the UDP header between the new IP header and the ESP header. As with transport mode, the UP header is initially configured with both source and destination ports of UDP port 4500, allowing for the translation of the source and destination IP and port information by a NAT device. Configuring a firewall to pass IPsec data. As you have determined whether your firewall supports IPsec, in other words, that your firewall is not performing NAT, or whether it supports IPsec NAT-T, you are ready to configure the necessary firewall rules. ESP and AH are protocols that are similar to TCP or UDP. When you define a firewall rule for ESP, you define that the protocol ID is protocol ID 50. Likewise for AH, you define the protocol ID to be protocol ID 51. You don't define ports as you would for a TCP or UDP based protocol, assuming that IPsec is used to protect all telnet traffic sent to the telnet server located at the IP address 192.168.22.44. The firewall rules shown in table 8.4 must be configured. Notice that you don't have to create firewall rules for the telnet protocol TCP port 23 because the data passing through the firewall is encrypted. IKE UDP ANI 500 192.168.22.44 500 allow. ESP ID 50 192.168.1.55 192.168.22.44 allow. AH ID 51 192.168.1.55 192.168.22.44 allow. If the telnet client and the telnet server support NAT-T traversal, then different rules are required to allow for the translation of UDP source ports as shown in table 8.5. NAT-D UDP ANI 192.168.22.44 500 allow. NAT-T UDP ANI 192.168.22.44 4500 allow. Tunneling through the internet. As people acquire faster connections to the internet from their homes by using digital subscriber line DSL or cable modem connections, the methods that people use to connect to their offices from home change. Why use a slow modem connection when you can connect directly over the internet by using your fast internet connection? For users with a fast connection, a tunneling or a virtual private network VPN solution fits the bill. Tunneling works like a dial-up connection, except that you gain the speed of your fast internet connection rather than send packets over a slow phone line. Data is encapsulated in a tunnel as it traverses the public network. Only when it reaches the tunnel endpoint is the data encapsulated and transmitted in its regular format on the network. Selecting a tunneling protocol. Two protocols are commonly used by tunnels when connecting to an office: point-to-point tunneling protocol PPTP and layer 2 tunneling protocol L2TP. Both solutions allow secure connectivity over a public network to a tunnel server, but have differences in their implementations. For example, PPTP uses Microsoft point-to-point encryption MPPE to provide encryption to transmitted data. On the other hand, L2TP has no built-in encryption algorithm. Instead, IPSec is used to encrypt the transmitted data. Table 8.6 shows the common decision factors considered when deciding between implementing PPTP or L2TP tunnel solutions. So figure 8.6 shows a remote client that can connect to two different tunnel servers, as you can see here. So VPN server 1 has IP address of 232.3.2.35, whereas VPN server 2 has an IP address of 172.168.1.211. Because PPTP can pass through any firewall solution that supports filters for protocol ID 47, the remote client can use PPTP to establish a tunnel to either VPN server. Likewise, if the remote access client and both VPN servers support NAT-D and NAT-T, L2TP IPsec may be used to connect to both VPN servers. If the remote access clients or VPN servers don't support NAT-D or NAT-T, L2TP can only be used to connect to VPN server 1. L2TP access to VPN server 2 is not possible in this case because the firewall at 39.200.1.2 is performing NAT on incoming traffic. So I'm going to leave it here today for this video. If you like listening, please consider like, share and subscribe. Thank you.